Hi, I am Y. Ashwin Karthik from India. After 10 years of intense research, I found a breakthrough for the next generation renewable energy technology. My innovation is the system for power generation using the kinetic energy of flowing water inside the multiple penstock. And I filed 3 patents on this technology. Before getting into my innovation, we need to understand the basic functions of an existing hydro power plant. The existing hydro power plant utilizes only the stored potential energy of the water inside the reservoir to rotate the turbine along with the alternator to produce power. In this existing system, the penstock act only as a water transport medium. In this illustrative system, the height of the reservoir is 6.26 meter, and the exit pipe diameter is 1 meter. If there is no penstock in the system, we can directly find the exit velocity of reservoir U by using the root of the 2GH formula. By applying all the derived values in the MGH formula, we get 532 kilowatt of power from the exit of the reservoir. In ideal conditions, this is what the power we get from the turbine. Now, let's look into my innovation. Our system is designed to harvest the gravitational kinetic energy in the penstock. From the kinetic energy definition, any mass moving with a velocity, it gains some kinetic energy. To bring the same mass to its rest state, the mass need to dissipate or transfer the kinetic energy to some other system. This basic principle is used in regenerative braking system in the electric vehicles. In this illustrative system, the height in penstock diameter is similar to the previous example, but the length of penstock is extended to 300 meter. So, its volume is 235 meter cube, which means nearly 235,000 kilogram of water inside the penstock. Due to the friction loss inside the 300 meter long penstock and various fittings, the flow velocity is reduced to 4 meter per second. When this huge mass of water moves at a 4 meter per second velocity, then it gained 1.87 megajoules of energy. In ideal condition, the Bernoulli's theorem states that the total mechanical energy of the flowing fluid, comprising the energy associated with fluid pressure, the gravitational potential energy of elevation, and the kinetic energy of fluid motion, remains constant. Torricelli's theorem states that the speed of a liquid, flowing under the force of gravity, out of an opening in a tank, is proportional jointly to the square root of the vertical distance h between the liquid surface and the center of the opening and to the square root of twice the acceleration caused by gravity, or simply u equal to root of 2gh. In real-time condition, the friction loss create head loss. Here, due to the friction loss inside the penstock, the flow velocity is reduced to 4 meter per second from 11.08 meter per second. Now, I will explain the gravitational kinetic energy with the help of 2 different cases, but the calculations are done in a similar way. For both cases, the velocity of water flow and the length of penstock are fixed as constant, only the diameter of penstock is variable. In case 1, the diameter is 0.03 meter. Due to its smaller diameter, the head loss is increased to 193 meter. Which means, 193 meter height of water level is required to push the 211 kilogram of water inside the 300 meter long pipe at a velocity of 4 meter per second. In case 1, the available power at the exit of reservoir is 82 kilowatt, which is very higher than the gravitational kinetic energy in the pipe. Just by increasing the diameter of pipe or penstock, we can reduce the head loss. In case 2, the diameter of penstock is increased to its maximum possible point to obtain the least head loss value. Here, the gravitational kinetic energy in the penstock is 6 times higher than the available power at the exit of reservoir. When the gate valve is in closed state, the volume of water inside the penstock have its own stored potential energy. At the moment of valve opening, the stored potential energy in the penstock and reservoir is instantly converted into kinetic energy. The large diameter penstocks are not capable to withstand the sudden pressure surge. That's why, here the diameter is optimized to 1 meter. In our system, there is a gate valve and a non-return valve. Initially both the valves are in closed position. To start the system, the gate valve is opened for a second. Instantly, the water flow reach its 4 meter per second velocity. Then immediately the gate valve is closed rapidly. Due to the sudden closure of gate valve, the pressure rises rapidly, and open the non-return valve and propel the turbine. Once the energy transfer is complete, then the water flow come to rest, and then again the gate valve is open and shut to harvest the gravitational kinetic energy. This is my simple illustrative novel design. To harvest linear power, the system uses multiple penstock that can be open and close one by one, as similar as the multi-cylinder IC engine. The starting procedure of this system is similar to the IC engine. For the first few minutes, the pumps and valves are activated using the external power source. The turbines, pumps and valves are synchronized all together by the ECU to achieve the closed loop. The synchronization process enables the system to maintain the predetermined water level of the primary reservoir. Once the alternator starts producing power, and then the pumps and valves utilize the power from the alternator. The rest of the produced power is exported to the national grid. The multiple valves enable the system to achieve the precise control over any conditions. This is a 10 megawatt power plant with 20 penstock design. Now, let's look at the real-time scientific math behind this 10 megawatt plant. Initially, we need to define the penstock dimensions, and then we need to find the head loss due to 300-meter long penstock and various fittings. H equal to K into V square by 2G is the formula for find the head loss due to various fittings. Where K is the constant value for a fitting, each fittings have different K value. In this power plant, a single penstock have various losses, such as head loss due to water entry into the penstock and water exit out of penstock, and T-joint loss, and a U-bend loss. In our system, at any given moment only the gate valve or a non-return valve is in open state. Both valves have similar K values, so here non-return valve K value alone is considered. To find head loss due to friction loss in 300-meter long pipe, we need to use the Darcy-Weisbach equation. To solve the Darcy-Weisbach equation, we need to find friction factor F. For the F value, we need to find Reynolds number and apply that value in the Colebrook-White equation. The Colebrook-White calculation uses an iterative process to solve for friction factor. After solving, now we have the HF value, 2.6949 meter. The total head loss is 6.2586 meter, or, it is the height of water level required to push the water inside the penstock, at 4 meter per second. To find discharge rate Q, we need to multiply the area of the cross-section of penstock and velocity V. Our system output depends on the kinetic energy. There is an energy gain in acceleration and energy loss in deceleration. If the gate valve is open for X second, the maximum discharged volume of water Q1 will equal to Q into GT, where Q is the discharge rate, GT is the time consumed by the gate valve for open and shut. In our system, the volume of water discharged from the gate valve is pumped back to the reservoir. Mass 1 is the mass of water discharged from the gate valve. If the gate valve is open for too long, then this system loses its synchronization. The non-return valve open state time T depends on the deceleration time, which means how long time the system takes to transfer the kinetic energy into electrical energy. If the non-return valve is open for X second, the maximum discharged volume of water Q2 will be half QT. At peak load condition, this power plant can transfer the energy in 1 second. So here T equals 1 second. In this 1 second deceleration occurs. Here mass 2 is the mass of water propels the turbine. If T second is reduced below the predefined 1 second, then the pressure will rise beyond our safety level. Now, we're going to calculate the maximum operating working pressure of the system. In our system, initially the potential energy in the reservoir and penstock is converted into kinetic energy. Then the available kinetic energy is converted into potential energy from the previous calculations. Now we know how much kinetic energy is available in a penstock, and also we know how much mass of water going to strike the turbine. By rearranging the kinetic energy and potential energy formula, we can find the pressure head or virtual height. After solving with the available values, we derive the pressure head value 122.3 meter, and after solving with the ρgh formula, This system's maximum working pressure will be 1.26 megapascal. Now, we will deduct the energy loss one by one, and deduct the energy consumed by the system one by one. Initially, we need deduct the strain energy losses. Due to the sudden pressure surge, the water get compressed in the penstock, and also the penstock expands a little bit. To find the strain energy loss, these are the standard formulas. After solving the formula with the available values, we get 0.14 megajoules as strain energy loss. Here, the NVPE is the potential energy required to divert the water, which is passed through non-return valve and turbine, back to the reservoir. So we need to calculate and deduct the energy required for this process. The efficiency of the megawatt turbine and the megawatt alternator is over 90%. After deducting the losses, we get 1.3 megajoules from the alternator. The mass of water which is discharged from the gate valves are pumped back to the reservoir. So we need to deduct the energy required for water pump. Up to 5% of energy is consumed by the valves, ECU and other auxiliary equipments, which is equivalent to 54 kilojoules. After deducting every possible losses, we can harvest up to 1 megajoules of energy from a single penstock. There are 20 penstock in this plant. Each penstock completes its one cycle in 2 seconds. T second is the non-return valve open state time. GT second is the gate valve open state time. Each penstock engage one by one with a time delay of 0.1 second. At peak load conditions in any given second, 10 penstock per second can deliver energy. So this system can generate 10 megawatt power. From this, I theoretically proved that this system can generate power from the gravitational kinetic energy. The favorable properties of fluid and gravity are wisely utilized in my novel design. Now, let's look at the impact. In large-scale power generation, my technology requires only less than 0.2 TMC of water to operate a 1000 megawatt plant for a year. A similar 1000 megawatt thermal power plant requires more than 1 TMC of water. Our technology require only 650 acre of land for the 1000 megawatt plant, whereas similar 1000 megawatt solar plant requires more than 3000 acre of land. By deploying advanced corrosion resistance technique and proper maintenance, our system can serve up to 100 years. So 100 years of return on investment. These are the real economics of the customer value proposition. Solar panels can generate power for 8 to 9 hours a day, and its lifespan is maximum 30 years. Wind turbines are idle at non-windy days, and its maximum lifespan is 25 years. Nuclear power plants need high initial capital and high maintenance cost. As per international nuclear policy, a nuclear power plant can kept operational only for 40 years. Hydropower plant requires a large land acquisition and high initial capital, but most of hydropower plants are operational only during monsoon seasons. My technology can generate consistent 24/7 power, within a small area of land, and with less volume of water and with less initial capital. So the estimated return on investment is very higher than all the existing power generation methods. That's why I call this technology as a disruptive technology. I hope now you will understand the potential and feasibility of my innovation. For further information and business collaboration, please contact immediately. I am really thankful for your golden time. Thank you so much, thank you.